I'm Sabetta Matsumoto, and in this video, we're going to be discussing the orbital mechanics that you get from central force potentials. First, we'll derive the general equation for the orbit, then focus on the special case of inverse square law forces and the Kepler orbit. In the last video, I introduced the effective potential is equal to L squared over 2 mu r squared plus U of r. Last time I mentioned that since it has a local minimum, there's a lot of interesting behavior we can get out of this system. Imagine I start with energy E1, which is greater than 0. This corresponds to an unbounded orbit. That means that I have only a single position where there is all potential energy and no kinetic energy. So this is a turning point of the system. So as we move in this potential, we start with some amount of kinetic energy and then move up the well of potential energy, losing kinetic energy to it. There's some point where I have only potential energy and no kinetic energy. And at this point, the R goes from R moving to the left to R moving to the right. And I continue moving in my potential like this. Since there's only one turning point in the system, this orbit is unbounded. These are often called scattering solutions, and these orbits look like this. So there's one position where I have R minimum, so I come into that position, I trade my kinetic energy for potential energy, and I turn around and I go off like this. Now imagine I have a system with energy E2, which is less than 0. This corresponds to a bounded orbit because there are two turning points, R min and R max, in my system. If I start in this system, I'm going to go back and forth between R min and R max forever. We're most familiar with inverse square law potentials, and these lead to elliptical orbits. And these are really nice because on these, there's a single position on my orbit where I achieve R min and a single position where I achieve R max. These cycle in this conic section forever. Since this repeats forever, we call this a closed orbit. However, virtually all potentials, aside from inverse square law and Hookean potentials, don't close. So for a general potential, there might be many positions where they achieve R min and R max throughout the course of their orbit, sometimes infinitely many positions. These orbits don't close up, so there's not a place where this orbit will necessarily repeat itself in time. In fact, the precession of Mercury, which is also not a closed orbit, pointed to there being a problem with the Newtonian formulation of gravitation, since there wasn't a closed orbit in places where they expected there to be one. However, it would be quite some time before the formulation of general relativity provided the correct solution. Now that we understand what behaviors to expect from different types of orbits, we'd like to solve for the path these orbits take for different central potentials. In the last video, I wrote down the equation of motion for a generic central force. Mu r double dot, so the force in the r direction, is equal to minus d by dr of u effective, where u effective is just the potential coming from my central force plus L squared over 2 mu r squared. And this here is the potential coming from conservation of angular momentum. This gives rise to our standard Newtonian formulation of this problem. Mu r double dot is equal to L squared over mu r cubed plus our central force. And we'd like to use this to solve for the shape of the orbit, which is r as a function of theta. And we're going to do that by using two different substitutions. The first substitution is a u substitution, where u is equal to 1 over r, or equivalently, r is equal to 1 over u. The second substitution is we'd like to change our derivatives from time-length derivatives into angular derivatives, and we can do so using the chain rule. which we've done many times before. So we've got d by dt is equal to d theta by dt times d by d theta. And d theta by dt is just our angular velocity, or theta dot. From conservation of angular momentum, we can rewrite this as L, which is our angular momentum, divided by our moment of inertia, or mu r squared, times d by d theta. And now we have to apply our u substitution to this, and we end up with L u squared over mu d by d theta. So this is, we've converted all of our time-like derivatives to angular derivatives. So let's have a look at r dot first. Under this formalism, we have r dot is equal to d by dt of 1 over u. And now we'd like to change our d by dt into this theta derivative, and we end up with L u squared over mu times d by d theta of 1 over u. When we take this derivative using the chain rule, we end up with minus 1 over u squared du by d theta. And I can combine these terms together, and I end up with minus L over mu du by d theta. And now we differentiate this again with respect to time to arrive at our double dot. So our double dot is going to be the time derivative of r dot. And this is equivalent to us writing this theta derivative of r dot. So this theta derivative is L u squared over mu times d by d theta of r dot, which is this term here, so minus L over mu du by d theta. These terms here are just constant, so I can pull them out, and I end up with minus L squared u squared over mu squared times d squared u by d theta squared. Plug this back into our equation of motion up here, I end up with this term here, which is kind of a mess. So I've got a whole bunch of constants out front. I've got minus mu L squared u squared over mu squared, d squared u by d theta squared is equal to L squared over mu times u cubed plus f of u. So let me divide through by all of these constants, and I end up with u double prime of theta is equal to minus u of theta minus mu over L squared u squared times f of u. So now I've converted this equation of motion into a second order ODE, which describes now the shape of all of our orbits. For the rest of this week, we're going to focus on the special case of inverse square law forces and the orbits that they make. The two main examples of this are Kepler orbits, coming from gravitation, and bound states of the hydrogen atom, coming from electrostatics. While I'm going to focus on the gravitational system, all of these ideas apply to the electrostatic analogs as well. In the case of gravitation, we have a force that is equal to minus g m1 m2 divided by their separation squared. I'm going to rewrite this as minus gamma divided by r squared. And this lets me consider any type of inverse square law force equivalently. All I would do is substitute in a different definition for gamma and potentially change the sign. In terms of my u substitution, this is just equal to minus gamma times u squared. The equation from my orbit now tells me that I've got u double prime is equal to minus u times mu L squared u squared times my force as a function of u, which is now minus gamma u squared. This is lovely because the two u squareds cancel out, and I end up with minus u times some constant, which is gamma mu divided by L squared. So this is basically comparing the strength of the radial force to the propensity for angular motion. This term here, gamma mu over L squared, has units of 1 over length, and we're going to be returning back to this constant a lot in the future. We're going to do one last u substitution. I'm going to say W is equal to u minus this constant. When I plug this into my equation, I just have the standard harmonic equation, and we end up with W as a function of theta is equal to some constant times cosine of theta minus delta. And most of the time, we can choose coordinate systems so that delta is equal to 0. I'm going to be doing that for the algebra in the rest of this video. When we go back to our U system, we end up with gamma mu divided by L squared plus some constant A times cosine of theta. Since A is just one of our constants of integration, it doesn't matter what A is, so I'm going to factor out gamma mu divided by L squared from that, and I end up with this constant gamma mu over L squared, 1 plus a new term, I'm going to call this epsilon, cosine theta. It turns out that since A has units of 1 over length, because W has to have units of 1 over length, and this gamma mu over L squared term has units of 1 over length, epsilon here is a dimensionless parameter that describes the motion of this particular system. And this term here, I'm going to replace this with 1 over C, where C now has units of length. That means that when I trade my U's in for R's, I end up with an equation for the shape of my orbit that looks like R as a function of theta is equal to C divided by 1 plus epsilon cosine theta. The first type of orbits we're going to look at are elliptical orbits. The equation for the shape of my orbit is R as a function of theta is C divided by 1 plus epsilon cosine theta. Let's just have a look at what happens when we vary epsilon. Cosine theta ranges between -1 and 1. When epsilon is less than 1, this term always remains positive. But when epsilon is greater than 1, then there is some position for which this term equals 0, which means the radius of my orbit is going to go to infinity. That tells me that when epsilon is less than 1, this corresponds to a bounded orbit. And when epsilon is greater than or equal to 1, we have an unbounded orbit. So let's focus on the first case where we have a bound orbit. The distance of closest approach, R min, is equal to C divided by 1 plus epsilon. So why is this? The largest this term down here can be is when cosine theta is at its largest, which is at 1. When this is at its largest, R of theta is going to be at its smallest. And equivalently, R max is going to be C divided by 1 minus epsilon. That's going to give us this type of cyclic repeating behavior where at theta is equal to 0, we start at R min, which is the distance of closest approach, and then at theta is equal to pi, we end up at our farthest position, and then so on and so forth. The distance of closest approach is called perigee, and the farthest distance is called apogee. And this is going to give us an elliptical orbit. This is one way of writing down an equation for this elliptical orbit. We can also do it implicitly using these different parameters. So A is the semi-major axis, so half the total length of the ellipse, and B here is the semi-minor axis, so that's half the total width of the ellipse, and D is the distance from the center of the ellipse to the origin. And we can write down an implicit equation here, x plus d squared divided by a squared, the semi-major axis, plus y squared divided by b squared, or the semi-minor axis, is equal to 1. For unbounded orbits, here we have epsilon that is greater than or equal to 1. In the case where epsilon is strictly greater than 1, we have an orbit that is now hyperbolic. For hyperbolic orbits, the radius diverges when 1 plus epsilon cosine theta is equal to 0. That gives us theta max is equal to the inverse cosine of minus 1 over epsilon. So what's happening here is that as we go through the orbit, the radius here is asymptotically approaching some straight line along here, and that's what defines this as being a hyperbolic orbit. Again, we can relate the implicit formula for this hyperbola to geometric distances in this problem. So here our distances are A, which is the distance between the point of closest approach and the place where these asymptotic lines converge. B is the distance between that point and this asymptotic line. And D is the distance between the origin of my coordinate system and the place where the asymptotic lines converge. So the implicit formula here is x minus d quantity squared divided by a squared plus y squared over b squared is equal to minus 1. In the case where epsilon is actually equal to 1, we have a parabolic orbit. This is actually going to happen with probability measure 0. For mathematical completeness, we'll include this. The radius diverges at theta is equal to plus or minus pi. So we don't have a sense in which we have asymptotic lines anymore. And in this case, we have an equation where y squared is equal to k squared minus 2kx. Now that we understand the shape of these orbits, let's have a look at how the eccentricity, or that parameter epsilon, affects their energy. At the distance of closest approach, the total energy is equal to U effective at R min. That's because at the distance of closest approach, there's no kinetic energy in the system. R min occurs at theta is equal to 0, which means that R min is equal to C divided by 1 plus epsilon, or equivalently L squared over gamma mu times 1 over 1 plus epsilon. Our total energy, which is equal to U effective at R min, is going to be minus gamma divided by R min, so the energy coming from our inverse square law potential, plus L squared over 2 mu R min squared. So this is the effective energy coming from conservation of angular momentum. Let me first pull out a factor of 2 R min. We end up with 1 over 2 R min times L squared over mu R min minus 2 gamma. Now let me plug in our definition of R min. So here I have quite a bit of nasty algebra. So I'm going to rearrange these quite a lot. I'm going to cancel out the L squareds and the mu's, and I can pull the 1 plus epsilon up to the top. And I end up with here gamma mu divided by 2L squared times 1 plus epsilon times gamma 1 plus epsilon minus 2 gamma. So now I can take away one of the gammas here, and I end up with a total energy that's equal to gamma mu divided by 2L squared times epsilon squared minus 1. What does this tell us? When we have an energy that is greater than 0, we have epsilon squared minus 1 is greater than 0, which corresponds to epsilon strictly greater than 0. We end up in one of these hyperbolic orbits. When our energy is equal to 0, we end up with epsilon equal to 1, and that's a parabolic orbit. When the energy is less than 0, epsilon squared is less than 1. So when energy is less than 0, that corresponds to one of our elliptic orbits. So I'm going to summarize all of these results into this chart. When I have an orbit that has eccentricity 0, I have energy less than 0, and a purely circular orbit. When I have epsilon between 0 and 1, the total energy is less than 0, and I have an elliptical orbit. When energy is equal to 0, epsilon is equal to 1, and I end up with a parabolic orbit. And finally, when the energy is greater than 0, epsilon is greater than 0, and I have a hyperbolic orbit. Now that we've shown that the energy of an orbit depends only on its eccentricity, in the next video, we're going to explore what happens when you inject energy into an orbit to change it. See you next time. All right, we're recording. But for the rest of blah, 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 to geometric now that the motorcycle goes by, to geometric distances. Oh my god. Seriously, guy.